So hello and welcome to reInvent. I'm Lena Smart. I'm the Chief Information Security Officer at MongoDB. I'm absolutely delighted to be here. I am going to stick to my script, otherwise I'll end up telling jokes and you don't want to hear my jokes. I have about 3 jokes. I might tell one later, we'll see. So you're here to learn about running MongoDB securely on AWS using field-level encryption. I am not here to be a salesperson. I'm the worst salesperson on the planet. But if you do want to learn more about our products, which are absolutely amazing, go to our booth and you can get socks, because I have socks. They are awesome socks. And also tattoos, which I was told after I almost put one on my face that they last about 2 weeks. So I'm glad I didn't do that. So we've got a really packed agenda. They've given me this, which I will break. Oh, there we go, it works. All right, let's keep hitting buttons. There we go. So we really have a packed agenda, and I'm going to get us started quickly. So I'm going to introduce Ken onto the stage in a few minutes, but first of all, I'm going to give a very quick introduction to our security practices and compliance. I'm also responsible for compliance at MongoDB, and I'm going to briefly go over our cloud database, our cloud-based database, Atlas, and there'll be questions at the end. So. Let's face it, there always has to be a privacy slide when it comes to security. It's just what we do. And our CTO, Elliot Horowitz, my boss, mentioned in his MongoDB World keynote earlier this year that some data is considered so sensitive that people are scared to put data in the cloud. To be honest, I think people are scared to put most data in the cloud. I think that things like field-level encryption are really going to change that for a lot of people. And field-level encryption is going to help you mitigate the risk of putting data in the cloud. It happens entirely on the client side. Field-level encryption is built into every MongoDB driver, and Ken will talk more about that. And it's transparent to developers. The MongoDB API doesn't change. And additionally, it's going to help your privacy program. So everyone is always looking to mature the privacy program. It's not the easiest thing in the world to do, but having field-level encryption will definitely help you with that. Wow, I just got really loud. Okay, sorry. One of the most powerful features of field-level encryption is how you select the encryption key. You have many options. You can have an encryption key per collection or per field. My personal favorite is an encryption key per user, and this is particularly powerful. It means that if I get fired, if I don't do this speech very well, the admin can search for all of my data very quickly, throw away that encryption key, which is kind of, crypto shred, and then it makes my data unreadable in every replica set and backup. So let's hope that doesn't happen. All right. So we have a lot of regulations and certifications, as I'm sure many of you have to go through. Before I worked at MongoDB, I worked in fintech, and before that, I worked for the power industry. So both very heavily regulated industries. So I've brought that knowledge, 20+ years knowledge, into MongoDB, and we are definitely working to mature a compliance program. So we've just aligned our entire compliance program with the NIST cybersecurity framework. I think it's important that you pick something that's got a common language that everyone can understand. I always find that it's a dry enough subject as it is, compliance and risk management. So if you bring in something like the cybersecurity framework, it's just a commonality of language that you can use with a whole bunch of people, from developers to security people to marketing people to whoever you need to talk to, your board. They all understand what you're talking about. So some of the different qualifications and regulations that we follow. GDPR, you all know what GDPR is. Do we have anyone from the UK in the room, apart from me? Oh, one person, yeah. We can talk later, probably over a large drink. We are HIPAA ready, where this enables us to offer to covered entities and their business associates the use of a secured cloud database environment to process, maintain, and store PHI, protected health information, so that's really important. That's your health information that has to be secured. The big one that we got earlier this year that I'm particularly proud of is ISO 27001. That was a lot of controls that we had to go through, over 300, which we now have to maintain as well. PCI DSS, for those of you who process credit card information, you'll know about that one. Our cloud service has been validated as PCI compliant. As I mentioned earlier, we are compliant with the NIST CSF. We've aligned our compliance program to the NIST CSF. And then finally, obviously we work with the federal government, and these federal agencies must evaluate the data that they hold, and they have to watch for the presence of sensitive data and then provide mechanisms to secure that data, and our tool sets help them with that task. So obviously, these compliance certifications, there's probably over 500 controls now that we have to meet and maintain, and it really does feel a bit like a root canal without Novocaine, so apologies if there's any auditors in the room. I used to be one, so I feel your pain. But with a managed solution, using field level encryption in Atlas helps our customers meet a lot of these legal and regulatory obligations as well. So we have a comprehensive monitoring feature and auditing capability, and our customers can gather all the evidence that they have to get to keep their controls up to date by using our software. So let's get very quickly acquainted with MongoDB Atlas. If this works, there we go. First thing is it's self-service and it's elastic. You can deploy, modify, and upgrade on demand. You are in control of your database destiny. It's global. We're available in 18 AWS regions covering the whole globe. And this is a great option for geolocation to comply with GDPR, for example. Some of you were just at the talk, the previous talk on Stitch, and we offer a serverless platform service, Stitch, which has database and authentication triggers to react to changes in real time. This is particularly so for customers who are looking for audit control, audit trail, all that kind of good stuff to keep the security program up to date and also just maintain that compliance control. We also have comprehensive monitoring, offers deep visibility into 100+ key performance indicators. Everyone loves KPIs. You can link this to something like Splunk and have the single pane of glass so you have visibility with your data in real time. We have managed backups with point-in-time data recovery, and my all-time favorite, enterprise-grade security is built in with role-based access control, LDAP integration, the whole 9 yards. So now that I've set the scene, I am going to introduce Ken White onto the stage. Ken is a security principal at MongoDB and is a senior member of my security team. So thank you. Over to you.
Thank you, Lena. Hopefully you get a glimpse from Lena's introduction on some of the work we've been doing the last few years to meet some of the most demanding requirements of some of the largest systems in the world. I think people may not necessarily be aware, but the largest healthcare companies, pharma, retail banks, investment banks, consumer tech, automotive, sort of, you name the industry, there are folks that are running critical workloads on our platform. And so as important as the compliance and regulatory standards are, in fact, they're table stakes in some respects, I want to take a little bit of time to kind of think about how, what our mental model is of database security, right? So there's lots of different ways we could carve this up, but sort of three core pillars of security that we tend to think about around authentication and authorization, so access controls, the way that we protect data on networks, and the way that we protect data at rest. So I think people are probably familiar with the term encryption in motion, or encryption in transit, and then encryption at rest. Those are the last two, and then identity and access we'll kind of dive into a bit here. So lots of different ways that we sort of demonstrate we're either the person or the service account that we claim to be. There can be credentials, simple passwords, it can be biometrics, bearer tokens, in the case of NTLM, in the Windows world, AD, Kerberos, and so forth. These are effectively contracts that say, I can present a certain piece of information, and a system that I'm trying to get access to identifies me as that, as having an authorized role for that. We have hardware supplements to that, so around the U2EF and the FIDO key standards that have kind of evolved. And then hardware mobile enclaves, right? So on our mobile phones, there's been a lot of evolution in terms of the protections that can be afforded for additional two-factor authentication. And of course, all these things, as people are evolving systems, are moving towards federated role-based access controls and single sign-on and so forth. All those are important. The network itself, so I think people know that sort of in the earliest form, and actually in some ways, there are still architectures that make sense to have data that are transferred between nodes within a system that are just using wire protocol, plain text, right? We evolved to SSL, and as we found protocol flaws, that kind of, the constructions and the protocol techniques themselves were sort of enhanced. And generally speaking, now when people make REST calls or web services calls, we're using TLS with forward secrecy. So the idea is that if an attacker or an adversary were to capture network information and somehow got a hold of keys, the time window around the period where those data could sort of be reversed or decrypted is going to be limited. Storage encryption. So there exists, obviously, hardware-level mechanisms on disks, on physical media. Most of the time, though, when we're talking about an encrypted database, what people actually mean is storage-level encryption, right? So in the case of Windows, this is BitLocker. In the case of most Linux deployments, it tends to be dencrypt and Lux. In the Apple world, File Vault, and so forth. So those are important protections. There do exist databases that allow you to do either table or collection level in the NoSQL world down to individual fields. And so some of these, in some respects, have been around for a while. In fact, I was talking to someone that I guess there were early versions of Lotus Notes that had a type of field level encryption. But it's critical to understand where that encryption happens. When we think about adversaries, when we think about attacks and breaches, the mental model that a lot of people have is, well, there's an outside, there's an outside attacker, there's an outside adversary. The source of trust, though, for most encrypted databases is a central model. The idea is that the people who are operating this system consider DBAs, system admins, infrastructure providers themselves. The notion is because of either performance reasons, doing backups, patches, security, patches and so forth, or by nature of the role of people's positions, they need to have access to certain information. And it can be confidential payloads, right? In the case of infrastructure providers, if you have access to the hypervisor, if you have access to the key management, if you have access to the compute node itself, at some level you're saying, well, we trust that to compute data, right? Let's take a mobile app, right? So I've got some sensitive financial information. I send it to the database. The database is encrypted. I'm meeting some compliance standards, so we're good. Well, what are some of the implications of having a central model like this? There's a whole digital sort of breadcrumb or ecosystem around any kind of data store, right? There are logs. We do snapshots. We do backups, right? There are temporary files that get built up over time. And then fundamentally, the process memory, at some level, most encrypted databases are operating on plain text. So what happens if you're in a privileged position to view into these? Well, you can get quite a bit of confidential information, and that may be a problem. So we shouldn't just think about outside adversaries. We should also consider what are the implied controls around our encrypted database. One approach that people have taken, and that we've looked at as well, is client-side encryption. The basic idea being that while data is in use, it's encrypted at the application level before it gets to the server, before it gets in maybe some context to a third party or some other provider, or maybe even on-premise where You have high-privileged administrators or DBAs that, because of the nature of their job, they need to have access to information, but maybe they don't need to have access to, say, the entire HR database. Maybe they don't need access to all medical records on a system to do their work. And so the notion of client-side encryption is encrypting it similar to the way that encrypted messengers work on your phone, right? So it doesn't matter who's intercepting, and it doesn't matter who's hosting it. It's been encrypted at the point of contact, and by the time it gets to the third party, it's already protected. We started this project about 2 years ago. So one of the things that we did was we had several conversations with clients, and this idea came up several times where we had customers that said, we're running large workloads. And so to give you a sense of that, I mean, we have some financial customers that are doing $60 billion a day on MongoDB. We host some of the biggest gaming platforms in the world. But sometimes those are lines of business, sometimes they're analytics sites, sometimes they're other, maybe they're mission systems, but they're not necessarily, running like super confidential workloads. Consider a record like this. Social security number, street address, maybe a phone, a mobile phone, maybe a healthcare record. That can be kind of scary to think about being sort of shipped to a third party that you trust. But how about if it looks like this? What if all those digital breadcrumbs and kind of the ecosystem around a data store look like this? Well, then it opens up a huge number of use cases, right? Because there are areas where it's not a matter of trust in the sense of I don't trust you as a person. It's from an institutional perspective. We can't tolerate a risk threshold for third-party providers working on these kind of sensitive data, payloads. But as soon as you sort of dip your toes into the water of encryption, you're faced with, well, maybe we have really sophisticated and experienced software engineers, but it doesn't take long to look at forums, and you see things like this. I've got a software development framework. I'm going to do something with AES, right? AES is good encryption. I'm going to use, 256-bit AES. Now I've got 27 different options of how I do that, and I don't know what it means, so maybe I'll just pick the first one. Or maybe I've read a few chapters into the book, and so I know that we should be using a certain type of authentication of that payload so that if someone tampers with it, we'll be able to detect it, or we'll be able to reject that data. But what if I do this on one platform like Python, and then I do it on Java, and I'm getting different results? These are tricky problems. One of the best quotes I've seen on this is from the founder of this social bookmarking site called Pinboard. People may know it. But it's a great quote, because what he gets to is, we've seen protocols where, in the last few years, and we're not talking about timing attacks or side channel attacks, because those are kind of academic. I'm talking about single bit level biases in decryption. Individual bits were enough to kind of unravel the thread to completely deconstruct and undermine the confidentiality of data. It's as if it's a fragile, complicated endeavor where, yeah, maybe there are software frameworks, maybe there are SDKs, maybe there are plugins, but it's hard to get things right, and it's hard to know the right choices. We don't want developers having to face that. What does this mean, encryption as a first-class service? In some respects, MongoDB's client-side field-level encryption isn't new. The fundamental building blocks have been around, in some cases, for 2 decades. If you have a web app now, or a web service, where you've got really confidential information sort of going back and forth, right now, today, in most languages, you can get some kind of software development kit, plug it in, make some of those choices on the options, and do things. The problem is, when we looked at this and when our customers looked at it, they said, we've got a lot of code. We don't want to have to rewrite our queries. We don't have to rewrite all of our applications. And by the way, a lot of SDKs allow us to encrypt data, and if we pull the entire record back, we can sort of decrypt it client-side, but we can't search it. So I don't really have a database anymore if I can't search. If we're doing if we're building sort of greenfield, if you ask a cryptographer, you're going to be running really sensitive payloads on a system. How would you build a client-side encryption? You get a lot different answers than if you're supporting, in some cases, 14-year-old legacy long-term distros, If you're supporting things where the system cryptography libraries may have been around for years and they're established, and you don't have some of the kind of newer or more modern constructions. Because MongoDB runs everywhere, and I mean everywhere. So our build system, something we call Evergreen, has something like 36 standard intersections of operating system, distro level, the hardware platform, so ARM, Intel, IBM Z-Series, and MongoDB supports 12 different languages officially, and in the broader ecosystem of developers, there's like 20 languages that are supported. Moving something from a simple kind of C-based library to something that can work both in Ruby and PHP and C# and Java and Go and Node and Python, that's a little tricky. And we wanted to make it as seamless as possible for developers no matter what language they're using. So where does it run? On MongoDB Atlas, if you're doing self-managed. If you've got mission workloads that, because of regulatory requirements, you've got to run on GovCloud, we can do it there. If it's on-prem use cases, it works there. We also made a lot of work to make sure that if you're a developer, you shouldn't have to have any internet connection. You should be able to be doing lots of development, really sophisticated kind of work without having to touch the internet at all in offline mode. So usually systems have a limited amount of confidential information. Let's say you're storing 300 or 400 different kinds of field records within a system. Maybe you want a single key. Maybe you want lots of keys. Maybe you want to have on a per user basis, per application user, maybe multiple keys per field depending on the use case. What you don't want to do is you don't want to have a full round trip, you don't want to have a full round trip to a key management service. So one of the best practices that Amazon advocates, and it's sort of generally accepted in the field, is the idea of envelope encryption. We'll get to that in just a second. From a developer's perspective, we took the JSON schema, which is it's existed for quite a while, but I'm not sure a lot of developers are aware of this. The basic idea is that within a flexible schema, you can say, I've got certain high data fidelity needs, and so for this field, it's got to be a date, and it's always got to be a date. Or this has to be a string, or maybe this is a number, and that's got to be between 1 and 100. So the JSON schema has existed for a while. It's not widely used, but it's sort of been there, and it's sort of a first-class citizen. We extended that with an encrypt property. What it means is that any field in a collection can be marked as encrypted. Keys can be done on a per field or per document basis. So there are some trade-offs though, right? If the database is suddenly oblivious or blind to the data that it's computing, you can't do things like geospatial. You can certainly encrypt a longitude and latitude and retrieve it back, that's fine, but you can't ask an encrypted database, give me everything within 5 kilometers of this encrypted field. It just doesn't work because it doesn't know the underlying sort of actual data for that first coordinate, and it also doesn't know the plain text for those nearby neighbors. Range queries. So you can't say, give me A through M of customers who have encrypted their last name. So there are some trade-offs that way. We'll offer different reference architectures on how to deal with that. It turns out there's lots of different options you can use, and some have really better performance profiles. You could do arrays, but you have to do it at a top level. So it's a little in the weeds, but arrays are similar to subdocuments in the sense of you can have multiple addresses, multiple properties, multiple contact numbers, that sort of thing. And so within the context of a subdocument, it's fully supported. Arrays, not so much unless you encrypt at the top level. There are certain types of aggregation pipeline filters, again, generally around things like limits of indexes on encryption where the database is kind of oblivious. In general, though, about 80% of the use cases we're seeing from customers, this fits really well. So the use cases you can imagine span everything from PII to HIPAA-controlled systems. Some of our first beta adopters on this program were dealing directly with patient care records and insurer data, so financial data as well. You can literally encrypt card data and search for that and use indexes on those. So you can You can say, I want this social security number, or I want this credit card number. There are lots of things in the industry now that sort of work around this by proxy and other things. If you've ever had to deal with a tokenization system or talk to an architect who has, they can be pretty painful. We didn't want to have to do that. We want to be able to make it a first-class citizen in the query itself. Easy to use. If you've got queries that are sort of optimized for CRUD applications, just simple insert, update, delete operations, you should be able to run that unmodified. We want strong security guarantees. As I mentioned, there's lots of different options in encryption, and there's classic kind of performance and sort of usability trade-offs with this. Customer managed keys. So it's crucial to understand those keys only live on the application side. They're never seen by the database. They're never seen by the DBAs or the admins, or in the case of MongoDB Atlas, by our staff as well. The content's opaque to the server and the server operator. Okay? How do we do it? So the key building blocks are IAM, KMS itself, and then within the system we use key stores. So the idea is that you can have maybe 1 or 100 or 1,000 or 1 million local keys that are part of your collection, and I'll show you how that works in just a second. KMS, I think folks are probably familiar in general with the service. It's high availability. There's a couple different options, but effectively it's a global service. It's backed by, certified hardware where in certain regulated contexts that really is crucial. Maybe if FIPS certification or the kind of things that, the use cases where you need cloud HSM, for example. So, as I mentioned, envelope encryption. I don't want to be making a lot of round trips to the key management service. The database should keep data as local as possible, as long as possible, to the extent that I know it's fresh. So what we use is this notion of envelope encryption. The idea is I've got a master key or multiple master keys, and they encrypt other keys. They encrypt data keys. Then we can store those keys en masse in your own collection. Now, why would you want to store data keys if you just told me you don't trust the database? They're encrypted data keys. If you trust AES to protect your data, you should trust AES to protect your keys. IAM. So lots of different ways to combine IAM policies, both for service accounts and for people accounts. Rules can be inherited and combined. So within the context of KMS, there's lots of different options. You can do directories, indexes, searches, all kinds of operations. We wanted to make it so that it's possible to have a key as narrowly scoped as possible, just a read just an encrypt or decrypt operation only. You can combine these together, as I said, to get a number of kind of sophisticated flexible access policies. So IAM effectively protects KMS, and there are lots of different ways to control that. Of course, there's the CloudTrail auditing capabilities. You can do origin whitelist on the key itself. So you can say, don't even allow a web service request to KMS to do an encrypt decrypt unless it's originating from this IP address. You can also do 2FA programmatically on KMS requests. I think a lot of folks may not be familiar with that. We've got some example code up on GitHub, links back to our docs. The service feature, rather, I should say, is still in beta. We've been previewing it for probably 4.5 months or so now. But effectively, the flow is this. You create a master key with minimal permissions. You create an IAM role. You assign the master key role to a service account. And then if you have people accounts, so for example, maybe you have a web service that calls KMS, but you've also got analysts where you want to individually manage their credentials or their time window for access to a project, you can do that as well. So let's consider, say, a billing system and app server. We've got 2 service accounts, different identities. In the case of people, those can be set at the top level. So maybe I only have access to billing records. Bob's got lab results, patient results, and so forth in this healthcare application. And then we've got a power user, Alice, who can see everything. Let's say we have a sensitive healthcare application. It's going to send PII-type data to MongoDB. When it sends it to the application, the MongoDB driver will intercept that and say, well, this collection's been marked as encrypted, so I need to do something with it. I need to go to the key store. I need to bring that back if it's not already cached. If I don't have it, or if this is the first time it's been requested, then I make it to KMS and I come back. Now that I've got that, I encrypt the data, and then I pass that on to the database. If you're looking at this as an administrator, so this is the Data Explorer view within MongoDB Atlas, but it would look the same if you were doing another kind of graphical admin tool, you'll just see binary data. So the underlying primitive data type is bin data. And so what that means is all your existing replication tools, so things like backups, imports, snapshots, all those things will continue to work because these are already known primitives within MongoDB. So in the earlier example, we had different people roles that were tied to these different IAM policies. You can also modify those on the fly. And so when that happens, not only are you limiting what is possible by policy or by procedure, you're technically limiting it too. You cannot decrypt that data if the person with that IAM role doesn't have access to the system. Quick note about cryptography. We'll be doing a couple of papers coming out probably in the next 2 weeks. I'll leave this here mostly for review and happy to talk to folks kind of in depth later. But the basic notion is we're calling out to the native operating system libraries for the crypto primitives. We didn't want to roll anything ourselves. If you trust Windows and the Windows domain, if you trust maybe Red Hat that has some kind of FIP certification around OpenSSL, you can continue to use those. If you have a Java application, NSS, or some other crypto provider, you'll continue to use. These are authenticated encryption techniques, which means the slightest alteration and the decryption fails. They're tamper resistant. They're both abuse resistant and misuse resistant. And more to say about that soon. One of the things I should say on this final bullet here, we think we're pretty good at building distributed systems. We've got like 500 or 600 engineers at MongoDB. A lot of them are really specialized, capable senior software engineers. But they're not cryptographers. They're not professional cryptographers. So one of the decisions we made very early on was we wanted to work with some of the best people in the field who break database encryption. We wanted to work with people who break authenticated encryption, and we wanted to work with people who work at the intersection of software, security, and cryptography. So things like buffer overflows, things like the way that keys are managed, the way that plaintext leaks might happen, the way that third-party libraries might have some kind of network profile or something to be aware of. And so we actually ended up working with 3 different teams. One group out of Brown University, I'm not sure if folks are familiar, but Senny Kamara and his team, they've done some pioneering work around encrypted search. And they've done a formal cryptanalysis of our client-side field-level encryption implementation. We worked with Kenny Patterson in the EU, who's been a co-author on some of the standards for authenticated encryption. And then lastly, JP Amasan and his firm, who did the crypto audit for Facebook's Libra crypto coin, has worked with us from the very beginning on the design phase, understanding the security properties, and then doing, as I said, a formal cryptanalysis. So we'll be publishing those probably in the next 2 weeks or so. So I'm a developer. What does this mean? There's basically 4 steps. You create a data key. You create a JSON schema that says, for this particular field, it should be a string, and the key associated with it is this. You can create that JSON schema either on the client or the server. You could do it on the server to make administration easier and do change control a little bit easier. But if you're really unsure or the security profile of the payloads that you're running are such that you have to have the strongest security guarantees possible, then you want to run that client side. You do a MongoDB client connection the way you always have, whether it's in the shell or through this language. And then you do your query. The driver will intercept those inserts, updates, deletes, and modify it on the fly using the associated keys and using the associated schema maps to do that translation. It happens seamlessly, kind of underneath the hood. Oh, that's odd. Well, if you can imagine, the left side said, find patients with a certain social security number, you can't actually ask the database for that, right? I can't ask the database for social security number 901, et cetera, because, well, one, it wouldn't match because they're encrypted, but two, you don't want that information in the logs, so you actually have to do real-time translation from this is the plain text to this is the encrypted value, although with this, you've kind of got the bonus of both here, I guess. How about performance? So I think folks are probably familiar with the TPC benchmarks. It's kind of a standard that's been used for 2 decades. ASIA spent quite a lot of time over the last year porting TPC to a NoSQL kind of model using a document sort of approach, but we wanted to come up with kind of a standardized way to do that. And that's been published in the ACM proceedings. We've got a couple peer-reviewed papers that look at that. And so we decided that actually may make sense to understand relatively when field-level encryption is turned on and when it's off, and depending on different query profiles, how that looks. And so we've got some benchmark data coming out pretty soon on that. The YCBS benchmarks, this is the Yahoo Cloud benchmarks. So Python on the top and then Java on the bottom. In a nutshell, if most of your operations are read-write heavy, that's sort of optimal. If you're doing, we had one customer that had an on-site consult. They were generating about 10,000 keys per second because of their particular use case. And it turns out that there is a performance hit. We saved them about 600% speed up with some optimization. But then we looked at the wall clock. It was only like 2 milliseconds. So yes, if you go from milliseconds to a few milliseconds, then in a batch context, you're probably not that sensitive to it. We really are trying to optimize the cache to limit the cost, both in terms of network cost and performance, but also just cost of the service calls to KMS. Interestingly, most Linux distros have a fairly moderate level of the SE Linux profile, or sort of the equivalent in different distros. We do this operation where when the driver sends a query, we analyze, we basically parse the NoSQL structure for that. So there's almost like I wouldn't say a formal grammar, but there's a formal parsing tree that we walk through. One of the biggest engineering efforts we did, we thought like 90% of the work was going to be around encryption itself, like the core cryptography. That was probably a fraction, like 5 or 10% of the work. What was a huge amount of the work was to take the NoSQL parsing engine, our query engine, moving it from a C++ code base to all these different languages. That's what took a lot of work. And so one of the ways that we do that is we make local domain socket calls. It turns out that on some distros, those are logging more aggressively than the database itself. The fact that you've asked for a local host lookup gets logged. So we're still working on some of our performance guidelines around that. What's the roadmap look like? Going forward, we're looking at cloud HSMs and KMIP integration. We've got some additional query features. So there's some things that are just fundamentally limitations of an encrypted system. There are other things that just need some additional engineering to sort of enable. So there's certain limitations on materialized views and things of that sort. But we feel these are all published on our documentation site. The vast majority of CRUD operations are fully supported from V1. We've had a lot of customers ask about key rotation, so that's sort of built into KMS. When you create a master key, you can say automatically rotate it like once a year or however many months. We had customers that came to us and said, yeah, but we want to be able to not only rotate keys, but rekey data that's encrypted within these larger collections. And so we're putting some improved tooling around that. Effectively, you could do it in about 10 lines of Python, but we wanted stronger security guarantees and integrity guarantees. Enhanced encryption search options. So most of the engineering over the last 2 years was taking the parsing engine and making it abstractable. But part of that process was also taking the encryption capability as a plugin. So we offer deterministic, we offer randomized encryption. I'll show you that in just a second. But more importantly, we've got a pluggable encryption option now for Mongo's data stores. So Lena talked about some of the advantages of the MongoDB cloud. our Atlas service, Stitch, some of our other platforms. I don't think most people in the room need to be convinced too much about the advantages of cloud. These are our capabilities. Security practices, protecting the confidentiality of data while it's in use is the key part of doing client-side encryption. You can leverage KMS and IAM with these local key stores. Client-side encryption allows it to be done as seamlessly as possible and transparent as possible to the developers. We think that's really powerful. Lots of different use cases. It's available in MongoDB 4.2. We've got some links here, quick start guides. I think we've got Java, Node, C#, Go, Python, and others are coming. We're literally updating sample code and docs each day. So please take it for a spin, try it out. We've been in beta, as I said, for about 3.5, 4 months. So we'll be releasing this to GA very, very soon. And I should also mention, all the core crypto framework is Apache licensed. So it's all up for review on GitHub. You can take a look. You can understand what we're doing, inspect it, give us feedback. We invite that and we welcome it. So we've been working really hard for the last 2 years. We're thrilled to show this to the world and happy to open up for questions. Thanks.